Okay, while olefin decrease, so clearly there is a secondary reaction. Yes.
Well, thank you very much for the presentation, for the discussion. And it's my pleasure to introduce the next speaker, Dr. Donald Cronauer, and he is a special term appointee in the Chemical Sciences and Engineering Division at Argonne National Lab, where he has worked on, among other things, photocatalysis, hydrotreating of lube oils, and the development of Fischer-Tropsch catalysts. He's a person that has worked very extensively with the Bert Davis Group, and we have enjoyed that collaboration very much. He has been a PI on DOE contracts, developing and testing process concepts to liquefy coal and shale oil. And while among the Amoco Corp, Gulf Oil Corp, and Argonne Chemical Co, he has served as a senior research scientist, researching contracts ranging from fundamental research to pilot-scale operation in areas of synthetic fuels, petroleum, and polymer additives. He has over 100 publications and numerous patents, and today he will be talking about preconditioning effects upon cobalt-containing Fischer-Tropsch catalysts. Please help me welcome Dr. Cronauer.
Chasing all the wires around, that sort of thing. And it's an interesting aspect with the government funding nowadays. I just got a note from Human Resources at Argonne, please phone home. I'm wondering. In any event, the talk today, preconditioning effects on cobalt-containing catalysts. They've been promoted and unpromoted. The work, as quoted here, is myself, Jeff Elam, Jeremy Croft, Joe Libera, but a major portion of this work was also involved with Bert and Gary Davis and the various people at CAER who provide much of the analytical aspects and that sort of thing. I'm basically going to be talking about, of course, Fischer-Tropsch chemistry. It's reaction carbon monoxide and hydrogen, as everybody here knows, and we'll pass on by. Cobalt deposit, the primary catalysts are the cobalt-based deposit on various oxides, alumina, silica, etc. The iron containing materials, ruthenium materials. I'm sticking purely with the cobalt and the preconditioning steps of that. The initial steps of the reaction is cobalt-3, O4 going to COO, going to the metal, and it is believed that the metal is the active actual catalyst that's going into it. The two aspects that I look at is a fixed bed reactor that was run after using hydrogen for the pre-treatment step, and TPR, temperature programmed reduction with Zanes, XAS, and that sort of thing that was done at Argonne National Labs. And again, to me, I got a lot of free analysis of the interaction with Bert and Gary and others here. The Fischer-Tropsch experiment, the experimental unit, small fixed bed unit, reactor in here. Primarily the feed consists of hydrogen and CO, pressure control, feed mass flow controllers. We fed no liquid, so it was just purely the CO and hydrogen go through the reactor, preheater, of course, that sort of thing, and a couple thermocouples in the middle of the bed that is actually about a ½ inch long, that sort of thing. 0.1 grams of catalyst. We run through some wet ice traps to pull out some of the material that maybe of a higher molecular weight, though we didn't really have any to speak of. We have the potential to go through a dry ice trap, but that always gave us problems. So let's say we avoided it. Back pressure control, a little bit of a trap, just more to observe what was going on in the reactor and the legs. The reduction step, and the reduction is exceptionally significant in using the cobalt catalyst. The original concept was do it at 350C, wait a while, it'll work beautifully, make whatever runs you want to make. It didn't work out that way, and that's the reason why we bent the project in this way. The temperature of the reduction phase, let's say the catalyst charge 0.1 grams of catalyst. We blended in with coarse alpha alumina to dissipate the heat, get it over a little bit of the zone of the reactor. Temperature 350 C or 400 degrees C. Atmospheric pressure, time at temperature about 6 hours. Takes about an hour to get up to temperature, ran it at whatever temperature, the 350 or the 400. Flow rate, kind of incidental, it's 100% hydrogen feed. Followed that up with Fischer-Tropsch runs in that same reactor. Of course, cooling overnight to get it down to the reaction temperature that we desire. Temperatures were on the high side, you might say, for Fischer-Tropsch reactions, but 220 through about 300 degrees C, 13, 14 atmospheres, 200 pounds pressure. It takes time to heat up to the reaction temperature. The reason for having 2 receivers to collect the gas samples and that sort of thing to line out. We held it at 2 hours at any individual temperature. CO hydrogen 2:1, nominal ratio. Flow rate is fairly high. And for practical purposes, when Gary's talking about running a 50% conversion, their flow rates are 1/10 of this, so we're getting very low flow rates or very high flow rate, short residence time in the reactor. CO conversion as a point is calculated as 100% minus the components that contain carbon in there and normalized to 100%. Generally speaking, the carbon balance was 95 to 99% in that range. Atomic layer, some of the catalysts, the original concept was to make catalyst that we prepared with atomic layer deposition. The ideal is to have a nice smooth catalyst, everything well formed, and to put promoters on in the same sort of a way. Now ALD is not an inexpensive way to do catalyst preps, but we were giving it a shot to see if we could get a better catalyst that was a major change. And as a summary, it wasn't. We prepared it in a unit that essentially you have high temperature, you deposit a layer of whatever the material may be, cobalt, in some cases alumina, and the platinum. The references are cited, Jeff Elam, etc. I'll let it pass by at this stage of the game. TPR, temperature programmed reduction, was carried out in the APS, Advanced Photon Source at Argonne Labs. X-ray beam going through the sample and analyzed as such. We use, quote, a 6-shooter, a cylinder with 6 samples of catalyst contained within it. This is held in place for a period of time, step, and run around in a circle. It's calibrated such that you are hitting the same point on each cycle around the 6 steps of the catalyst. It went from room temperature to roughly 800 degrees C, about 1.2 degrees per minute. It was a very small sample of catalyst for the transparency of the X-ray. 3 milligrams of catalyst. It's running at 1 atmosphere and a hydrogen flow process. The X-ray absorption, again, Gary would be the better person to answer the questions in looking at this. Hexanes is the initial area in the absorption versus energy. It gives the types of central atoms, oxidation step, that sort of thing. The X-AS has such things as the number of neighboring atoms, the distance to neighboring atoms, the types, and that. This is where I got the free analytical aspects of the thing. I, in essence, passed it along to Gary, and lo and behold, magic numbers appeared afterwards. And I greatly appreciated that. My primary aspects were the catalytic reactor aspects. You start out at low conversion levels, and you have an iron reactor, stainless steel reactor. If you have the stainless steel reactor itself, you get a degree of conversion over the temperature range, either with an alpha alumina catalyst or an empty reactor. We coated that stainless steel reactor with a little bit of alumina by APS, or by ALD. You'll notice that it knocks down the amount of conversion so that we have a low level of background during the run. In some of the comparison of materials, ALD cobalt deposition versus incipient wetness, IWI it should be. The incipient wetness was carried out at CAER labs. 0.1 grams catalyst. This is basically an introduction slide. 400 degrees C reduction, the higher temperature. And you'll notice in going down the scale, again, empty reactor, 9% cobalt, the 11% cobalt, 17, 25, and the idealism of the ALD giving a better catalyst is rather well demonstrated here. Incipient wetness at 15% was more effective in a conversion of CO conversion versus temperature than the ALD prepared catalyst. So we went to more emphasis on the addition of the promoters. Now, looking at the difference between 350 and 400 degrees C reduction. In going from the background reactor, 350, 400 at the 9%, these were the incipient wetness cobalt catalyst. The 17, promoted, unpromoted, promoted, unpromoted, this being the CAER catalyst. Pardon me, these were the ALD catalysts. You can see an obvious step improvement with even the low levels of cobalt, promoter. In looking at the APS scans, you can see the observed reactions, the CO3, O4 to COO to the metal, and going down as time progresses along. These are individual scans. Photon energy versus absorptivity. In the analysis of the materials, the COO3 comes down, has a major step, and essentially falls off at roughly 400, 450 degrees C. the intermediate oxide going up and again falling off, and the actual metallic form of cobalt, averaging, let's say, around 600 degrees centigrade before it's really active, 50% activity, if you want to call it that, in this plot. Now, that's 15%. In looking at 25% cobalt on aluminum, essentially, you can go back and forth. There's no real effect of going from 15 to 25%. You essentially have the same curve, and sets of curves. You're talking about 590 or relatively high temperature pretreatment is necessary in order to make a good active catalyst. Now, our challenge with Reactor is we're kind of limited to 400, 425, 450 degrees C, and the comment was, well, wait longer. Well, we waited 6 hours, and no, it wouldn't seem to work. In looking at 0.1 gram of catalyst charge, the 15% at 350, well, again, the reactor itself, 350, 400, we're talking about that significant change. And going up to the CAR, the incipient wetness catalyst was much more effective. When we take 0.5% platinum and add it to the catalyst, where we were going without the platinum promoter, similar sorts of curves as presented previously. The 0.5%, we're up at about 450 degrees C for that 50% conversion or to the metal itself as the active component. The 0.5% is a greatly significant change in that promoter, and again, the 450 degrees C is the important point. Going backwards. Don't hold the button down. Okay, thank you. The effect of the platinum, the ideal thing at this stage of the game was to go to 0.1% and to put it on by APS, or the ALD approach. Various curves are shown. We have 17%. We do have the original one. This is 17% cobalt that was actually placed by ALD deposition on top of an alumina that was in turn placed on a silica catalyst. The 17%, you'll see down in here, the step of going up in the temperatures from 350 to 400 here, putting on 2% platinum, you have a significant change, and going up to 400, it's really taking off exponentially with temperature. However, again, going up with the catalyst with 2%, 400, we have a very high, 2% platinum that is, we have a very high level of conversion. The tendency, if you extrapolate the curves, is going down in a very different process, if you want to call it that, or different mechanism than is apparent otherwise than our series. So the taking the 2% platinum gave us a problem. In looking at the Arrhenius plots, again, the log of CO conversion versus reciprocal temperature, the activation energy in looking at the ALD deposited cobalt 400, 450, you're talking in this range. And when we went to the 2%, a very different activation energy. In here, the activation energy is in the order of about 30 kilograms, or 30 kilocalories per gram mole, and up at the 2% platinum, it's about 14 or 15. Again, indicating a different mechanism. Comparison of some supports. We did look at silica and 25% silica. You're down in here. We looked at the cobalt on alumina. It appeared to be of no difference. However, when we did put the platinum on it, you had a very major difference in going with the silica supported catalyst versus the aluminum supported catalyst. Comparison of sources, again, a similar sort of, and let me pass by at this stage again, get a little close on time. At various catalysts, looking at the 0.1% platinum, the 0.1% did not make a major difference in comparison, and comparing that to the 0.5%. These are shown purely to show that we're looking at an overlap of within the error bar. Generally speaking, the catalysts need the temperature of the 450, but at the 0.1% cobalt or platinum is very strong in supporting the activity of the catalyst. Conclusions and observations. The most effective Fischer-Tropsch catalyst was that of the cobalt deposited on silica or alumina with the platinum promoter 0.5%. The most effective technique is incipient wetness, by far more active catalyst than the ALD approach, which of course would cost more anyway. The addition of platinum promoted the catalyst. This is true for both the ALD and the incipient wetness prepared catalyst. The 2% platinum appeared high. It appeared to be a change of mechanism purely based on the Arrhenius plots and that sort of thing. The TPR gave an understanding of, and its use in Zanes and XAS is a very effective way to follow the course of the catalyst and how it reduces. Preconditioning operated 400 degrees C or higher. And as a general background, which is consistent with everyone else's work, cobalt conversion increases about linear with CO conversion, in essence, is linear with cobalt content in the range of this 9 to 25. A couple oddball things to look at. There is no effective cobalt concentration in this, going from 15 to 25% for the general activation to reduction phase. There appeared to be no increase, even though the reactor was held at 350 for this 6 hours. When we did come back and rerun at 400 degrees C, reactivate, it did take a further reduction. So it was kind of like at 350 you could hold it forever and you had a certain level of catalyst activity. You had to take it essentially to the 400 to get the next step in reactivity. And ALD is believed to provide a uniform surface but even at 0.1% platinum, the promotional effects, in essence, were very effective, but it's not a strong indication that you have an even coating on the cattle. Acknowledgements. I'd like to acknowledge the help of Chris Marshall, Ted Krause at Argonne, of course Gary and Bert. Argonne was supported by funding of DOE. The Advanced Photon Source has additional funding, and the various individuals who are associated, or the individual companies that are associated with the APS work, or the APS lab. Thank you.
Thank you very much for a great talk. We have time for questions.
Yes.
Thank you for a nice talk. I'm actually interested in the support effect on the reduction behavior. So it's well known that on alumina you would delay the reduction of the cobalt, but this is also strongly morphology dependent. So I was wondering actually two related questions. First of all, what is the kind of morphology of the oxide that you make by ALD?
It is believed to be the gamma alumina.
The cobalt oxide.
Oh, the cobalt oxide? CO304.
But the morphology, would it be a layer covering?
It would be layered upon layer upon layer upon layer.
Because the second question is actually, I was surprised that you didn't see when you get a thicker layer, let's say 25%, that it didn't affect the reduction anymore, because it's generally believed that cobalt small particles are more affected by the support interaction than big particles. So
I agree.
That's why I was surprised by the result.
I agree. And
actually, there are some XRD results of some of the catalysts, and when from what I remember, when the ALD was done on the silica catalyst, it actually had a very broad peak in XRD, and the crystallites were much smaller than what you would observe with impregnation on silica. Remember, I was showing at dinner, I don't know if you saw that, but the impregnation of cobalt on silica, there were very large particles compared to alumina. But when Dr. Cronauer and his colleagues did the ALD on silica, cobalt was much smaller, and the cobalt oxide was much smaller, well dispersed, and interacted more with the support. And that's why he's seeing, when you add platinum, you get a higher extent of reduction of cobalt on silica. Whereas if you add platinum to cobalt silica prepared by IWI, since it's already, you have big clusters, it already reduces at low temperature. And so when you add platinum, it's not really effective.
The silica, the support effect is not so big.
Yeah, I mean, the support effect we mainly see with the IWI technique. But when they're doing the ALD method, the interaction is there with both silica and alumina.
Okay.
Yeah.
The method, I guess, relies on that.
Yes, yes.
yes.
We have one more question from Professor Paul.
Yes.
The selectivity, the definition is always of much interest. I wonder whether from your research you see some relation what you are doing to the methane selectivity. Is it sensitive to it or not?
Within the range that we worked, methane was, I think the carbon yields were in the order of 3 to 5%, and more or less uniform. It was one of these things that you have your bucket of money and you spend your research and the bucket is gone. And some of those sorts of analyses would have been interesting to look at or follow up on. But no, I just didn't get that far.
Well, if there are no more questions, please help me thank Professor Cronauer again.